next on Venus stage, Build Stuff menu, we have a talk about the big quantum theory and Azure story. And André Melancia is next to me, Azure and IoT trainer, SQL. He's going to talk, said to me to make a short presentation about him. So let's listen to what he has to tell. And everyone watching us online, have your questions at Pine. And in the audience, we can do it the live questions. So, round of applause for André, and he'll start.
Okay. Thank you, everyone. Thank you very much. Okay, welcome. So first of all, how many of you here know advanced physics? Only one, two. Okay, don't worry, you're not going to need it. I'm assuming most of you are developers or related to IT, and this is why we're here. We're going to talk about a session that covers quantum, but specifically for IT. Okay, so this is my small introduction because of the theme of the conference. Everyone is doing this. So has anyone figured out what the bits and bytes do here? What does this mean? Okay, so you still haven't... Famous Mortal Kombat moves, okay. The one you have in mind, and you can see that in the recording later, it will have something different. Okay, so we'll see what happens. Okay, and big welcome everyone being here. You are very brave because you are in a session that says quantum, so that's crazy enough. But this is a technology that's actually a set of technologies that we're going to use in the future. Maybe not today. Well, you can use it today, but maybe in 5 years' time this will be normal. Okay, so remember that 5 years ago, people were doing things like no one was actually doing machine learning, and suddenly 5 years ago people started to use a lot of machine learning. This is not a new technology, but people started to use machine learning 5 years ago, and now everyone is doing it. So think about in 5 years' time, everyone is going to be doing quantum in one way or the other. The current scenario is that the barrier is the price, but you can already do some simulations using a normal computer, and then if you need to use it, actually use it and process a lot of things, you can use physical hardware that's already available. A bit expensive at this moment, but 5 years from now it will probably be very cheap. Okay? So anyway, who am I? My name is André Melancia, I'm from Portugal, and yes, I am here in person, which is actually really good. So thank you all for being here in person, but also thank you to everyone remotely. I will be happy to take any questions that you have, so just ask. This is how things work. And if you go to my website at andy.pt, there's going to be a link there that jumps to the presentations. Once I do the presentation later on today, maybe tomorrow, I will publish it, and you will be able to see it, but mostly the video when it comes out is the better way to have a look at this. Okay, so important question that everyone considered before joining the session. So who here has this intelligence level? Anyone knows this guy? Who's this guy? Sheldon. Okay, exactly. So we don't need to be as intelligent as this guy to understand this session. We might need to be intelligent as this guy, who doesn't seem intelligent at all, to understand this session. So this guy had a 155 IQ, and he is obviously the guy that came up with relativity and a whole bunch of things that we are now proving to be true 100 years later. So this is obviously a very famous guy. Anyone know the name? I forgot. So obviously Einstein. Okay, this guy is a bit more difficult. Do you know this guy? Okay, Richard Feynman, exactly. So Richard Feynman is also a physicist, but he's funny thing, he is one of the earliest hackers I've ever seen. So I've read this book, actually this exact book. It says, what does it say there? Something by Bill Gates. So introduction by Bill Gates, but in reality this book was from the 80s and I read it when I was something like 15, something like that. And there's a lot of interesting things here, not just about physics, but about life in general. So this is the original hacker guy that does social hacking, breaks into safes in military installations and things like that. This is a very intelligent guy as well, and many of the things that we're going to talk about today, I'm not going to really specify which ones, but many of the things about physics were actually done by this guy, okay? This guy predicted what could be done at this moment, okay? And he did that, before the 80s. So he died many years ago, but in the 80s and before he predicted most of these things. So Richard Feynman. And of course, you don't need to be any of these people or have this level of intelligence. We would all hope to have this level of intelligence, but all the level of intelligence we need for this session is, who is this guy? Steward. Okay, so all we need to be is stewards, so that's fine. Okay, so let's talk about quantum and what we can do as developers to actually do stuff with quantum. But let's start from the beginning. So obviously, what's our first things that we did for computing? Well, we started to count with our fingers. That's what we do when we grow. The first thing we learn is how to count with our fingers. This is what Neanderthals did that thousands of years ago. But after that, they came up with interesting techniques. So you had that abacus thing, which is like a big machine with a lot of balls going to the left or to the right, so you'd be able to count it. That's probably the first calculator that we know of, and this is thousands of years old. And then we started to use things like mechanical machines. So if you still go to some places like some shops, they might still have some registration machines that you get, they print you the piece of paper that you get with a bill, and it's fully mechanical. Okay, but then obviously starting in the 50s, 60s, and so on, mostly 70s, we started to have normal electronics. We started to have actual computers, and this is pretty much where I came in. Late 80s, beginning of 90s, I started to use computers myself. And these computers at the time were very basic. You had very simple computers. Most people, when they learned how to do programming, they were actually having a look at things like assembly, which pretty much no one does these days. It's just too scary to have a look at assembly. If you consider the Windows stack or the Linux stack, going all the way down to assembly, that seems very scary. But we'll get to this because it's going to get more than scary of this. Okay, so we started to have some really nice CPUs. So if you consider things like the 8086 CPU and 8088, which is even only 8 bits, these kind of CPUs were very basic to program, but then on top of that, they added more things. And then even the hardware itself became much more complicated. You had things like the 486, now you have the Pentiums, now you have the i5, i7, even i9 kind of things, and those have a lot of intelligence inside the actual chip. Okay. Now, I'm not going to expect that in 5 years we'll have a chip the size of the other chips that does quantum. I don't expect that. At present time, quantum machines are, big, right? These are big, the size of, I don't know, maybe a car, but flipped 90 degrees, something like that. These are currently very big, but maybe in 5 years' time they will be slightly smaller, and then 10 years' time even smaller. So gradually we will see things like quantum, but on a smaller and smaller scale. How much? No idea. We'll see. Okay, but 30 years ago, no one expected to have things like a computer like this. This is 1,000 times better than the computer that took people to the moon, right? 1,000, maybe 1,000,000 times faster, right? I have no idea, but it's much faster, and it fits in your pocket. It has all of the things that you need. This kind of thing has better resolution than my normal computer, might even have more memory, and it's as small as this. So you get that quantum might also be used in a small amount of things as well. Okay, so I did mention that about 5 years ago it became trendy to start using machine learning. Nowadays, most companies that do anything related to IT will use machine learning in one way or the other, right? You don't know this, but if you're using PowerPoint like I am now, you are already using machine learning. For instance, you use machine learning if you put up an image in PowerPoint, and they will go to cognitive services and detects what's in the image, and they will give you an alt text for accessibility purposes that tells you exactly what it is. You don't even know it, and you are using it. Okay. So, but quantum can be used for different things. So that's our future. That's our next line. And what we have now is, oh, a lot of people looking at me. I'm not sure if this is a good thing. Okay. You know I'm wanted by the police, right? And don't tell anyone I'm here. I'm kidding. Anyway, let's continue. Nothing to do with the police joke, by the way. Okay, so let's do a comparison between a traditional way of doing programming and the quantum way of doing programming, because it's not the same. In a traditional way, what do we use in a traditional programming style? What do we use? Any ideas? Just say anything you want. Sorry? Binary, exactly. Zeros and ones, right? Is there only zeros and ones? Okay. Anyone from electronics? No? Okay. So most people who are in IT but studied IT and computers, they only care about zeros and ones. If you are in electronics, you usually care about zeros, ones, and the third state, which is unconnected states, right? So this is actually one of the bases for most computers. You always have three states. The one, the zero, and then you have the third state. But we'll get to that. Okay, so you have... In the traditional sense, you have bits, so binary, zeros, ones, and the third state. In qubits, you have something different. I'm not going to bring this up now, otherwise you'll just run away, okay? It's not that bad. I'm not going to tell anything about maths, okay? Please don't worry. So this will be simpler. Otherwise, I wouldn't even understand it myself. Okay, with bits, it's easy. It's either a 0 or a 1, so we understand how this works. But with quantum, there's always an uncertainty. It's never 100%. There's a probability that that particle is there. So you probably heard that you can measure the speed of a particle or the position of a particle, but you cannot measure both, right? Heisenberg's uncertainty principle and other related things. So it's complicated, right? There's always a cat in the mix as well, but that's a different story. Okay, so reading a qubit might invalidate the state, or might it? Probably will. So that means once you read it, it becomes a random value. But at least you can read it first. But then you have to do something, because in a normal environment like a normal computer, when you read a bit from a hardware bus, the bit's still there. You can read it as many times as you want. But in the quantum world, when you read it once, it disappears. Now, this is a problem for all of us, because, if you have a memory and the memory disappears, it's like an elephant. An elephant never forgets, but what does an elephant have to remember? It's complicated. But anyway, we'll see some techniques that we use to get around this problem, okay? So anyway, one of the things that happens is that you can actually take the quantum states that exists, and they came up with some interesting techniques to actually preserve the state in some ways, but at the same time give us access to the information. We'll see how this works, but the idea here is whatever you do, you don't work at that very low level. You try to abstract yourself and work a bit higher, but we'll see about this. Anyway, just to mention a few usages for current things nowadays. So before you had normal programming, you did things like information systems. You would go and try to, use them normally, just put information in, get information out, query that, figure out if someone owes money or something like that, and then, normal stuff. But then we started to use AI and machine learning, so obviously we know that everything now is based on machine learning. If you go to Facebook, that goes terribly wrong, because every time you post something that says it goes against community standards or something, because AI gone terribly bad, even someone that said something like sorry, that is considered against community standards. standard. So if you do it wrong, that goes terribly wrong. But if you do it right, it's a big advantage for everyone. Specifically, you have usages for machine learning in the health field. So things like predicting cancer, things like predicting any other kind of disease, actually. Simple things that you probably use today to actually get here. So I got here using, I'm not going to mention the name. It's not a taxi, it's one of the other apps. So I used one of those. So this works really well. There's a car there somewhere, and then there's machine learning, and machine learning will find a way to find the closest taxi to there, and then take that taxi, well, not a taxi, the other thing, take it to the destination that are requested. And they will try to optimize this as best as possible. It's not first come, first serve. They will actually choose from all of the people there, and they will recommend which one is best and then suggest that to people a few seconds, 1 or 2 seconds before they suggest to other people. Okay? Just because they prefer to have that specific person, which is the closest one, to answer the call as fast as possible. But anyway, things like doing traffic, you know that doing traffic is a crazy thing. It's basically an optimizational problem because if you try to figure out traffic with 10 cars, that's easy. There's 10 cars in the road, you figure out the problem. In a normal city, especially a capital like Vilnius, you are supposed to have 1,000 cars in a road at any given time and an hour of traffic. If you try to comprehend all of the variables, it's difficult. Now, I really respect the people who do machine learning. I do machine learning a lot, but not at this level. This is just crazy advanced. And they do a lot of machine learning into detecting not what's the best path to find from here to there, but what's the best path now from here to the next place, and then from here to the next place, and then from here to the next place, but with 5 minutes difference each time. Because the rules might change. Traffic might go somewhere else. Okay, we as humans, we know, oh, all the traffic is going this direction. So if you go in this direction here, I did this last time, it worked very well. But this is difficult to have a computer understand this, okay? These kind of problems like traffic, some other problems like, let's say, cryptography. You want to crack cryptography. That's especially difficult. This is why quantum is also very good. You can do a lot of quantum computing into cryptography and actually hack the thing, but we'll get there. But the idea here is that you have a lot of problems, especially optimizational problems, in which you need to have a lot of computing being used to handle this problem. How do you use it? Well, you can use AI, machine learning. You can do that in the cloud, and the cloud has a lot of capacity. You pay for it, that's fine. But what if you want that capacity to be as fast as possible? There is a limit to what the cloud does as well, right? One of the alternatives is to use things like quantum, and quantum is able to handle a problem very, very quickly, but with some limitations I'll mention just in a second. But these limitations over time, they will disappear, and this will be very effective. Okay, usages for quantum. So similar usages. So I've seen people use quantum for machine learning. I've seen them being used just for simple things like turning on and off a bit, which is what you do with IoT. So when you get an IoT example, the first thing you do is you have a LED, turn it on, turn it off. This is pretty much what you do in quantum when you get started. Okay, nothing wrong with that. You're getting started. It's like doing a print hello world or something like that. This is what you do for the first time. But after that, there's a lot of things that you can do, and there's even libraries now for machine learning using quantum. Okay, so you might expect, oh, machine learning is very complex. Can you use quantum and machine learning at the same time? The answer is yes. If you have enough computational capacity, you can do it. Okay. Now, as I mentioned, some of the problems are related to optimization, and optimization is if you have a problem with a lot of variables, and in this case, traffic is a really good example. You need to fix that problem. You need to find out a good solution, not just for you, but maybe for other people in the road as well, because, you know, most algorithms now are one-to-one. So you don't care about anyone else. You just care about yourself. You want to do what's best for you, and everyone is in competition with each other. But if you are able to do that, that's fine. You can use optimization for this, but that would be even better if you have a centralized system where everyone talk to each other and they organize themselves into doing a lot better. And obviously you can still do that with normal cloud nowadays, normal machine learning, but if you use quantum, it's much faster. The reaction time would be faster. Okay? So anyway, health, we talked about this, traffic management, and even things like just faster machine learning. So if you go to YouTube, they give you a recommendation maybe once a week about the things that you want to see. So if you see the same videos, same recommendation 1 week later, or whatever time it is, they will give you different recommendations for the video. They still do real-time recommendations, but those cost a lot of money as well. Okay, if you use Quantum, yes, it still costs a lot of money, but you can do it, so it's not really much of a problem. Okay, Skynets. Well, I'll leave that for future reference. It might happen, okay? But quantum cryptography. So here, I actually divide this into two parts. You now can do cryptography using quantum, so you have particles. You entangle the particles. So let me mention entanglement. So if you have a particle, there is ways for you to entangle two particles, and specifically, let's say that we're talking about 2 qubits, which is not a bit, it's something different. I'll explain exactly what it is in a second. But let's say you have 2 qubits with values. If you break them apart, if you give that to one person, if you give that to a different person on the other side of the world, on the other side of the universe even, if one person opens the quantum bit and tries to read it, that bit which we didn't know what the value was, it suddenly gets defined. And the other person on the other side will have, as long as it's quantum entangled, they will have the exact same bits. There is applications here for cryptography. I even see applications here for data transfer, which is something that people have been working on. So this is not as linear as you might think, which is, oh, quantum is just a technology. It's actually a lot of things. You can use this for storing data. You can use this for processing data. You can use this for transferring data from A to B. And the funny thing is, and I don't want to go into a discussion about this because it's too much physics, and whatever discussion it is, I will lose because I'm not an expert in physics. But if you have particles that are entangled in some way, if they are farther apart, what I've seen from some experiments, I'm not sure if they're entirely proven, but what I've seen is that the particles, when they have values, they don't really respect the passing of one side to the other. They don't respect the speed of light, apparently, okay? So they get updated immediately, which is very strange for us because we are assuming that we are limited by Einstein's logic of the speed of light is the maximum speed for transfer of information. Okay, so there's things here that even us as humans, we're still not at the level of understanding. So we are trying out to use a technology we don't fully understand. When we try to use bits and bytes, we understood voltage, we understood everything that happened in the electronics world. We knew this. We didn't understand things higher level when we tried to minimize the size of things, but we understood it at a high level. But we are using quantum, but we still don't understand how every piece in the quantum world actually works. Okay, we'll get there and things will improve, so this will improve as well. But the idea here is that what I'm trying to show you in a second is that things are a bit higher level, and we will be able to use it no matter how much the physical implementation of the technology will work. At the higher level, we'll use it the same way, and that's the important part. Okay? So anyway, cryptography cracking, that's the second part I wanted to mention about cryptography, which is, think about this. Nowadays, you have cryptography for everything, like home banking and stuff like that. It's supposed to be secure. It protects lives, it protects your privacy, it protects your money, etc. So if you have the possibility of having a huge machine that's allowed to, crack things very quickly, all of the mathematics that you thought would take, 2,000 years or something like that to crack that thing, or use a very big computer and maybe take 1 year, but that would still be very inefficient. With quantum computing, you might be able to do that much, much quicker. Okay, and that is scary for us. That is scary for everyone. That's why things like governments, like the NSA, like all of those government agencies everywhere are really worried about quantum because it might change the logic into spy stuff. Okay, so they are worried about this, but especially most people are worried about what's going to happen in the normal world we live in, especially since the pandemic. Everyone's at home. Everyone trusts security. Okay, there's been hacks. Security has improved. TLS has improved a few versions from SSL. We consider that stable, but if we have a player like Quantum, the old games are change. So that's going to be a problem. Okay, so bits. So let's have a look at bits and try to understand how bits actually work. So I did mention this, so 0, 1, and the third state, which is the disconnected states. And all of the bits are very easy to measure. You have a multimeter or something, you are able to measure. If it's from 0 to something like 1 volt, 0.71 volt, that would mean that it's a 0. If it is from typically 2 volts to anything to 5 volts, that will be a 1. If it's simply not connected, that's a third state, which is highly used in electronics. Okay, but with qubits, that's different. Oh, sorry, that's different. But all of this, you will get a guarantee of the value. So let's say you don't have 5 volts, you have 5.5 volts. You don't have that, you have 3 volts. Everything just works. Okay. But let's have a look at what happens with quantum. Okay. So with quantum, this will be slightly different. Anyway, just to mention that when you have CPUs, you have things like assembly. And this is, I'm assuming most of you, even if you don't use it every day because you're not expected to use it every day, at least you tried it, right? You've seen it once, maybe in university, something like that. You tried it once. And obviously, you can do it, you know, the building blocks, you can add values to a registry, etc. So at the lowest level, this is what you get in quantum, but hopefully you don't have to program at this level, you will program at a much higher level. So these kind of things are things that you can expect in quantum computing. Anyway, if you grow bigger, you start to have things like an operating system on top of whatever you need to program, and then you have that operating system will have calls, and then you ask for those calls. You don't really worry about the bits and bytes at a low level. You have some libraries and drivers and things like that, and then you have higher level programming languages. So you have things like C#, you have Java, you have any other language, right? And if you go to the quantum world, you can use things like Python, you can use things like Q#, which is quantum sharp. So you can use those programming languages at a very high level and actually create your own libraries to handle quantum stuff, okay? You don't have to be at that very low level and worry about, oh, I'm not sure, but if I read this, the bit will disappear or the qubit will disappear. Okay, just do an abstraction at a higher level, work with things that you can trust, so it's a higher level, and then from that point on, things will just work, okay? So print hello worlds in a normal computer would just take maybe 100 instructions in normal, normal assembly. If it is in quantum, that's going to be the exact same problem, maybe 1,000, something like that. But that's going to be a problem. Okay, so far, people are scared at this moment, hopefully, or like the cat, hope not. Anyway, think about this. After the session, it's lunch, so it's not that bad. Okay, so let's see what we have. So we have qubits, and I have some links. I'll actually go to the links. I'll leave this here, but then I'll go to the links directly. Okay. So let me just go and see some of the links and try to explain it. Okay, I'm not going to explain anything about the maths and the physics. It's not really my objective, but consider this. All of this is in Wikipedia, qubits from Wikipedia, simple enough. Okay, and what's a qubit? Well, it looks like this. It's like a big ball, three-dimensional, okay, where you can take that. Let me just point this here. It's easier for everyone at home as well. So you can just see that there is actually 2 vectors for everything. It's not just linear 0 or 1. It's actually a position of a particle pointing to a specific place. By the way, if you are scared, don't worry. But here's the general idea. Here you have a weird symbol that says 0, a weird symbol that says 1. If the particle is pointing up in this case, and this is just a convention, and it doesn't have to be this way, if it's pointing this way, it's a 0, if it's pointing that way, is a 1. Okay? But what if it's pointing, so let's say 1 is up here, but if I'm pointing this way, it's still 0. If I'm pointing this way, it's still 0. But they're 90 degrees apart, which seems strange, right? But still works. So there's a lot of tricks. So it's not just having 2 levels in quantum. You can make it simple and just assume it's a 0 or 1. That's fine. But you have extras in quantum, okay? So the way you use them, it's entirely up to you. There's in a normal environment with bits, you have gates. You have AND gates, OR gates, NOT gates, XOR, etc. You have all of these gates. Here, it's exactly the same. Okay. By the way, let me just mention for representation how you do it. So if you have a bit, a 0 bit will look like this. So let me just go and zoom this. So a 0 bit has this, pipe thing and then greater than symbol there. They're usually called the Dirac or bracket, which for me is just brackets, But yeah, they use this kind of technique. So this is a 0, this is a 1. They represent itself. So if you use things like linear algebra, you know how to do math with this kind of thing. So with this kind of vector or matrix, if you prefer. So this would be a 0 here would be a 1 on top and a 0 on the bottom. This would be a 0 and then a 1 in the bottom. Don't worry too much about it. This is okay. Anyway, if you have two states, you can mix 0, 0, and they will look something like this. 0, 1, they will look something like this. There is a reason. I'm not going to explain this now, but there is a mathematical reason why they look something the ways of this. Okay. But anyway, what I wanted to mention is that depending on how you do things, and please don't look at the math, it's just scary. Depends on how you do this, you can move the particles and point the particles to a different location. Turn zeros to a 1 and things like that. But how do you do it? Well, there is something called gates, and not Bill Gates. So you have logic gates, and logic gates are something that looks similar to this. So this is fairly easy to understand in a graphical diagram where you have ands and ors. But how do these actually work? Well, I'm going to mention just a few. So for instance, this is an example of a gate quantum adder. So you have A and B. If you want to add 0 or 1 in A and 0 or 1 in B, so you add this, so you have a gate here, another gate here, all of this. So the input is going to be A and B and carry in. So let's say that this was part of a multi-bit adder, right? And then you have, let's say this is 0, let's say this is also 0, and then if you have 1 and 0 here, this was going to be 1 and 0, and then some is going to be, or the carry out, let's call it like that, that's also going to be 0. But if A and B are 1, this will also be 1 here, or something like that, okay? It's just a normal adder that you have in normal digital systems worlds. But here you can do this with logic gates. Now let me show you a few of them that make sense. So the identity gate is easy. So if you want to see what it is, you just ask for the thing, you get the result back. Remember that some of these things actually mean that when you read from the things, the original state kind of disappears. So there are some of these that actually, so when you do this and try to read it, you get the value out, but you kind of lose the original value in some cases, okay? So how do you do it? There are some gates next to this. I'll show you just one or two. These are too many, that have the result of the operation, let's say mixing the operation, doing a not, doing something else, but they will still keep the original value, so you can keep the other value if you need it for something else, okay? The original value. So there's something called polygates, and these are just X, Y, and Z, they just call them that. So X just means that you have a not, so that means you invert the gate, so a 0 becomes a 1, and 1 becomes a 0, so that's easy enough. Poly Z is interesting because it leaves the state unchanged, but it maps that. So graphically in 3D, it's still, if it's a 0, points to the top somewhere, one of those. If it's a 1, still points to the bottom, but with different 3D location. It points it to somewhere else, okay? It's still 0, it's still 1, but it points to a different location. Why can this be useful? Well, sometimes you have to mix multiple particles, and this can be useful for advanced things, but don't worry too much about it. This is just an example. Anyway, controlled gates. Controlled gates are always very interesting because you take 2 or more bits. The first bit is always a control bit. So if you've seen things in electronics, you have things like cable select or chip selects, which is a thing that says if it's 0, you don't touch anything. If it's 1, suddenly you do the operation. Okay, it's like a on-off switch. Okay, so the first qubit is always the on-off switch. So this one just says a NOT gate, so you have the inputs, whatever comes out. If it's 0 on the first bit, the other bit remains unchanged. If it's 1, it changes the other bits. Okay, so technically this is very similar to an XOR in practical terms. But yeah, anyway, there's 1 or 2 which are interesting. Some of these have the output of the truth table, which seems interesting as well. So in this case, you have a CC NOT gate, which is basically saying that if the inputs, the first 2 inputs are 1, if they're not the 2 at the same time 1, nothing changes in the rests. But if the two of them are 1, that means that the state will change slightly. That means that a 1 turns into a 0 and vice versa. Okay? Why do you need it like this? Well, there are reasons why you need 2 gates instead of just 1. It's a different kind of usage. Now, this kind of usage, there's more swap gates. It swaps the information. For instance, if these numbers are different, they swap 0 to 1 and 1 to 0. It might be useful for some things. There is one special gate which is used a lot and can be used a lot. Okay, which is this one, which is the Hadamard gates, which in the end generates a random number. So that means if you apply the gates to a qubit, doesn't really matter what the state was inside, the remaining qubit has 50-50 chance of being a 0 or being a 1. It's a completely randomizer, okay? So you have pseudo-random stuff that you use in computers nowadays. Sometimes you base yourself on the timer of the computer to make it a bit more random, but this is quantum random, okay? And this is used a lot, especially if you use this for things like cryptography, etc. You might be able to do random numbers very quickly so that you can try to generate random numbers and then verify if the numbers are okay to be part of a key, okay? But there's much more you can do with this. Now, we have limited time, so I'm not going to spend much time talking about the theory. There is things that you can use with Q#. If you prefer Python, you can use Python instead. All of this is okay. I'm just going to show you 1 or 2 things of how you can do this. Well, there is the quantum documentation. You go to docs.microsoft.com, Azure Quantum. Okay, so you will be able to see most of this, but I will show you how this works. So if you go to Azure, by the way, how many of you use Azure? Okay, 50% of the people. If you don't use Azure, get it for free. Okay, so if you go here and you go to azure.com/free, okay, easy enough. And you get it for free for 50 days. If you work in or study in universities, you get some free credit as well. Just use your university email account. That works well, and then you will be able to try some of these. Well, quantum might be expensive. So how do you use quantum? So you press the plus sign in the Azure portal. You say quantum. Oh, quantum. Okay, and then you have Azure Quantum here. All you have to do is to say, oh, I need to create an Azure Quantum, so that's the easy part. You select the subscription that you want to use, you create a resource group. I'm not going to do that now. Just give it a name, and then you need a storage account to store some of the information that you use, of course, right? But apart from that, all you have to do is to choose that, then the providers. I will show you the providers a bit later, but then all you have to do is to say create, okay? Obviously, validation failed. I didn't enter the names. I've already created the quantum environment here, so I will use it, okay? And this is what you get. So you get a quantum environment. It doesn't look much, but basically all you have to do is to have notebooks, so you can create your code in notebooks and then have it run in the providers. So what are the providers? Let me show you this. So by default, you have a provider which is Microsoft QIO, which is the default provider, probably the cheapest one, and you can do a lot of things like optimization, simulation, etc. There's a lot of different tooling that you can use here. But if you want to add a provider, and don't be scared, this is expensive, okay? So you have things like Honeywell, IONQ, one cloud optimization, etc. Let's have a look at this one. Don't be scared. Don't be scared. This is very expensive. So it starts at 125,000 per month. So you get this, even if you put this in euros, it's still expensive. And this one premium is a bit more expensive. So this one is clearly expensive. However, if you try a different one, they have pay-as-you-go. So this one will have things like pay-as-you-go, and they will have things like price 0.000 per 1 gate shot. This seems much cheaper, right? I think this becomes cheaper because we see a lot of zeros and we think we're not going to use it. But consider that there are millions of operations running a normal computer running Windows every second, okay? So you can spend a lot of money very quickly if you have a very high level programming, okay? It can get expensive, but remember, you are using this in hardware, okay? And this is difficult. By the way, remember that in hardware, there's another requirement as well. I will show you some notebooks, one or two notebooks, at least one, but let me just mention a requirement, which is when you run one of these experiments in quantum, it's not always the right choice. So it's a good idea to run it 2 or 3 times and then get a statistical result out. If most of the results go to, let's say your result was to get a qubit, 0 or 1, for instance, a simple thing. If most of the results say it's going to be a 1, let's say 80% say it's going to be a 1, but then 20% say it's going to be a 0, it's probably going to be a 1, right? But still remember, you are still dealing with probabilities. You might have to run this multiple times to actually have it work. Now, if you go to the notebook gallery here, you'll see that there's a lot of notebooks here, and they will explain the technology that they use. So Q#, Python, and then they explain that they use IonQ as the provider, so you will need to run things in that provider. Some of these you can first see things in a simulated environment and then actually run in the hardware. Okay, this one that says parallel, I will actually show you this one, and this one is fairly simple. So in terms of computing, I think most of you probably seen notebooks already, maybe associated with machine learning, but this is associated with quantum, but it's the same thing. So you use a Q# language, and in this case you have a language that simply tells you, let's create a function. And this function says sample a random generator. So they specify how many bits do you want to sample? And you say 1, 2, 3, whatever number you want. And then they say register is equal to a new number of bits. And then you say that for each of those bits you apply something to those bits. In this case, it's an age gate, which is a Hadamard gate, which is the randomizer gate, right? So let's say I'm going to run this one. This will just take a few seconds. While this runs, I'll explain the rest. So workspace reloads, so that's fine. It will do something like that. And then simulates random sample number, qubits is equal to 3. And this will give you some results. Now I'm running the first one. I will run the second one and the third one as soon as this one is finished. I think it's finished already. Oh no, yeah. So this is finished. So I'll run this one now. Number 2. The other one was from before. So if you run this, you get 3 qubits. It says 0, 1, 0, but if you run it again, as many times as you want, they will change. So it's a random change. Sometimes they repeat because, honestly, there are only 3 bits. There's a limited number of combinations that you can do here, up to 8, so yeah. But you will get all of this. But suddenly, this becomes scary as you go here. Try it in Azure Quantum. So you connect to the thing, and then you have to use the IonQ simulator. So that becomes interesting because now you start to pay the actual money. So the first part, you can simulate it, that's easy. You can do the rest in a very easy way, but that becomes a bit more expensive. I'm not going to do that one now. It would also take a bit of time, plus cost a lot of money, but you can try it out. Most companies that want to do quantum now because they want to be at the cutting edge, they will invest money in this, but as a normal person like you or me, it's going to be difficult for you to actually pay that for learning, right? But in any case, you can do the simulation using Q#, using Python, etc., and that will work quite as well. Anyway, there are some links here, so you'll have the video later. I will have my presentation in andy.pt. Okay, you will be able to see the links there as well. But in any case, hopefully this wasn't too much complicated for everyone. I tried not to use math too much. I know it's scary. By the way, I stole this slide from a presentation that was done in February this year. This is from someone at Microsoft. The name is there. So I stole the slide, but I gave it proper credits. And there's a lot more resources for you to try to use Azure Quantum. There's actually a quantum workshop that you can take. Just follow some of these links and you will be able to try this out and see this like a full day workshop, etc. At least 4 hours or something. So it's a bit more time. Anyway, a question. Is the cat going up or down? Who says up? One person says up. Who says down? More people say down. Well, the correct answer is down because you have the things from the stairs. Let me just go here. These things, it's like the thing from the stairs, the stone, right? So you can tell the cat is going down. Okay, yeah. Anyway. I think this is pretty much the end of the presentation. I really want to thank you all for being here, and obviously I needed to include the cats. Schrodinger's cat is the most famous thing in physics, so yes, of course, we need to have a cat here. Plus, all my presentations include cats, so it has to be. So anyway, thank you all for being here, and well, let me know if you use quantum, how you feel about it, and let's see what happens. Let's do quantum stuff, okay? If you use it for hacking, please let me know. Those interest me especially. Okay? Thank you all very much.
Thank you, André. A great presentation, really. Who wants to try Azure and Quantum now? Who would like to? If it wasn't the price, there are a few. I know you can't code.
You can still use the simulated one, so that's okay. Remember that even in the beginning, when we started to use cloud, we saw a lot of things about cloud. People were scared to use it because it had a price. So things like the free tier, etc., are actually useful. Using the free tier, you can still try out some of the quantum stuff with the simulation only, but without actually using the hardware. So that's fine. Okay, but given time, you will be able to use hardware. This is not perfect, but they said the same about machine learning a few years ago. Required a lot of CPU, but nowadays, everyone uses it. So in a few years, this is normal. Don't worry. I really hope that you will be able to use this in the next few years. Okay?
So if there are any questions now, if no, let's go grab some lunch and you can catch André on the way, I guess, and have some more questions. So